Today we are going to be looking at accumulation. So we're still using that integration, that area under the curve, but we're going to actually start with introducing this fundamental theorem of calculus. Now, if you need to take a pause and read through this or read through this on your notes, I would encourage you to. But the reason why this has such a weighty name is because it's very important. So fundamental theorem of calculus feels like a big deal because what this does is this connects differential and integral calculus. So what we have been doing up until this point is differential calculus, or like the study of derivatives using calculus to define instant rate of change. We are now moving towards some integration, which is like the antiderivative. And right now, we've really just been thinking of integration of area under the curve. But now we're going to start to make connections saying that if you have a continuous function, you can actually have the integral of it and find that area under the curve, which is very exciting. So here's the fundamental theorem of calculus. It is important to get this written down in your notes. And what this states is if f of x is continuous on the interval a to b, then g of x is the same thing as the integration of its derivative function. So that feels like pretty strange. So I'm going to give you guys a little example just to kind of see what that looks like. So let's take our function. Let's take our function f of t. And the reason we use t is because we're substituting this x in, so we need a different variable. So let's say we have some sort of a curve. I don't care what it looks like. And this right here is y equals f of t. What this is saying is for any interval from a to x, right? So here we're making sure we're continuous over that a to b interval, which we are. And let's say that we draw a value, right? So we're starting at a and we're going all the way to x. So let's just give us a random, here we go. So that area under the curve would be from a to x. Now, what this is saying right here is x is in between a and b, and it's also differentiable. Then we're saying that the value, right, this value of g of x can be found by taking the integral from a to x of this function, because what we would be doing is substituting, right, that x and that a in and finding that area from one side to the other. The alternate way is by saying that you have this idea where you're like, it all stems from this idea of like f of x, f prime of x would be the same thing as f of x, right? So we're connecting this whole idea of an antiderivative. And what we're saying here is if I take the derivative of x, of f with respect to x, that's the same thing as canceling out, right? We're taking the derivative of, but in this scenario, it's very similar, but we already defined g of x. This would be the same thing as saying that this is not g of x, this is capital F of x, right? Because we're saying that like these two things are correlated. So if f of x is the same thing as this integral here, this comes from taking the derivative of both sides. So if I differentiated f with respect to x, so differentiating f with respect to x, that'd be the same thing as differentiating, since these two are equivalent, right? We're differentiating with respect to x, all of this stuff right here, and that all is equivalent to f of x. There's some great resources on Google if you want to like see more examples of this, but for sake of time, we're going to be moving on. Reach out to your teacher though if this feels like weird or you want to see more, or just like hold on and wait till we go through some examples. So our first function here in example 1 is it's saying like, let's let g of x equal the area under this f of t curve, right, from -6 to x. And the reason we use x is because like we are changing this regarding what we're inputting. So for example, if I'm looking for g of -3, right, I'm looking for the area from -6 to -3. This is important because this helps define like our start and end point for solving these values. We know since our start point is -6, that is not moving, that we're going to be finding the area to the right of -6. So for our very first value, we'd be going from -6 all the way to -3. And here is where this kind of starts becoming, I think we talked a little bit about this in classes like fifth grade math with calculus, right? So we are finding those areas of these shapes, but we're using these really fancy symbols. So the whole idea is to like not overthink it. So right here, the first thing I would do is I would probably divide this up into shapes that I can like really get a good idea. I know from -6 to -4, there's a trapezoid, so I can get that area pretty quickly. You have a base of 1, 1, 2, a base of 3, and a height of 2. So if I have 1/2 b1 plus b2, when I get that, I should get an area of 4. And then I'm going to use a second trapezoid right here from -4 to -3. And when I calculate the area for that trapezoid, I get, let's see, 3, -2.75. And I'm just using that trapezoidal formula. So that 1/2 b1 plus b2 times height. And remember, for your trapezoids, I'm going to draw this again. Sometimes we forget. Your b1 and your b2 are actually going to be those y values, and your h is like your width or your x distance. So all I'm doing here for this -3 is I'm just adding these guys together. So this is going to be the same thing as that first area plus that second area, that 2.75. And so I know the value of my original function, g of -3, the output would be 6.75. I'm only going to do one more of these. The whole point is that you can go on and do this many different times. Also, there is no rule saying that you have to use trapezoids. If you want to use rectangles and triangles, that's fine. Trapezoids to me feel the quickest, but it's literally not a requirement. So when I get this done, and just for points, I used right here, just to clarify, I used 3, and I estimated that as 2.5 as that like B2 that I used for that trapezoid. That's going to be important for these other values. So let's look at G of 4. What I would look for G of 4 is we would want this first area here. We're wanting this gray area that I just found. I'm going to make another trapezoid, a third trapezoid, getting myself to 0. And then I'm going to do like a fourth trapezoid, getting myself to +4. And again, you can do this however you want. But if I am using these, so a height of 2.5, a height of 1, a base of 2.5, a base of 1, and this height right here would be a 3. Remember, we're using just like how long that is. I'm not using negative signs here. So when I solve that, I get that this area is 5.25. And then when I get this last trapezoid, I'll show the calculations here. We have a 1, and then we're going all the way 1, 2, 3, 4, 5, and then this guy is 4. So we'd have 1/2 times 1 plus 5 times that height, which is 4. And when I get that done, I get that this area is 12. So G of 4 is the area under the curve from -6 all the way up to 4. And when I add all of these areas together, 4 plus 2.75 plus 5.25 plus 12, I get 24. This starts giving me ideas about my original function, and we're going to explore this like a little bit more, but the whole idea is you start getting these ordered pairs on your original function, and you can start getting an idea of a graph of like the distance traveled or total accumulation. Looking at this next example, here's where we're going to start using that and applying it. It first asked me to complete the table of values for G. Because this is an integral from 0 to x, this is nice. I know I'm starting at 0. So all these shapes, it looks like I'm moving up at a distance, 0, 1, 2, 3, 6, 7. Oh, great. Okay. So if I look, we have 0, 2, 3, we go all the way to 6, and then to 7. So I'm dividing these shapes up, and I'm actually going to find those areas really quick. So take a pause and find those areas and get them written down in your notes. All right, I'm hoping that you have something that looks like this. So when I am starting to plug this in, I know that an input of 0 would be the integration from 0 to 0. Well, from 0 to 0, we've gone nowhere, so my output is going to be 0, 0 area. From 0 to 1, that area under the curve is just going to be like this first rectangle right here, which has an area of 2. From 0 to 2, we're going all the way to the second guy, right, which is a rectangle and a trapezoid added together, which is a total area of 5. For 3, we are adding in that other triangle. And when I do that, for that 3, I get that total area of 7. Here's where you have to be a little careful for 6. Because this is area underneath the x-axis, this is negative area. So when I do this, you have that 7, and then we have a 4, but because it's below the x-axis, it's like a negative 4. So this gives me a total area of 3. Then for that last value, that's 7, you're also including that negative 1, which gives me an area of 2. All this means is that we can start moving this and pulling this all together to start getting an idea of what our function looks like. My first ordered pair is 0, 0 for my antiderivative or my integrated function. My next ordered pair is 1, 2, right? Because my input was 1, my output was 2. When my input was 2, my output was 5. When my input was 3, my output was 7. And then 6, 3, and 7, 2. After I get these guys graphed, we need to connect, right? Because we know that this is a continuous function, so it has these values here. These were also straight lines, so you can start taking those ideas that you learned when you graphed, that like when you're moving back and forth, that like the derivative of a curve gives you that straight line. So we can kind of use this to manipulate like an idea of what I think this should look like, right? So we have kind of like a curve going on here, and then we're going to curve down. And remember, it does not have to be beautiful. It does not have to be perfect. I am not a great drawer, as most of you guys know. So remember, it does not have to be perfect, but let's label that y equals g of x. We can also draw some conclusions very similar to what we did in Unit 5, where the interval, so where g of x, capital G, is increasing, is where g prime of x is greater than 0 on this interval 0, let's make it open, to 3. So let's just make this is increasing when I realized my AP answer was, or my answer was not a great AP answer, where that g prime, let's actually make that a capital G so that we're really showing that strong connection, is greater than 0. Then it has a maximum value, very similar. G has a maximum value where, and let's go back, we are using f, so let's name that, where f changes signs from positive to negative, very similar to what we did last unit, at x equals 3. And then we can say the max is 7. And then we're done. Because if I look at this, we're like, okay, we're changing from positive to negative, so that is where that maximum is going to occur. Here's where this stuff starts to get pretty fun. And this gives us a starting point. So very similar to what we did earlier, we would be adding, right? So like f of 2, we know it's the area up to 2. Now, this is not giving us that integral notation that we really love, right? We're not like, okay, I know where I'm starting, but it does give us some information. It tells us that f of negative 3 is negative 8. So what that means is that we kind of got this benchmark starting line, at -3. And what that means is that we're starting, here's that -3. So we're integrating from this point. So we're moving values to the right, we're adding, right? And then values to the left, we're subtracting. So this essentially became like our new y-axis in a way. And the interesting thing about this is if it gives me a value, so if I go back to that first guy, I did not have a value. I'm assuming that I'm starting at 0 and adding, but because it gives me this benchmark value, then I know that I'm starting at -8. Anything to the right, I'm going to be adding. So -8 plus area is going to give me values to the right. And if I'm going, so I want a value that's below -3, I would be saying -8 minus the area because we have that new benchmark, that like new axis of start. So for our first one, I'm going to highlight that -8 so I can like really see what's going on. We're just going to do 2 of these very quickly. If I'm doing +2, I know that here's my +2. We're starting off with that -8. And then from that -8, since +2 is to the right of -3, I'm adding that 10 and 26 to get a cumulative of 28. For something like -5, we're still starting off with that -8, right? And then we're moving to the left, so we already know this, right? Like I said, this is literally 5th grade math with calculus added. We're adding that area to the left, which is 18. So we're subtracting. So we're subtracting 18 to get an output of -26. Now, very similar to last unit, we can start using this information to graph, because if we have information about the derivative, we can graph that original function or that antiderivative or the integral. Wow, it's all coming together so beautifully. So I already filled out some of this, but I'm going to start using this information to get an idea of this graph. I know that from -3 to -1, we are increasing, and that slope is positive, which means we are concave up. From -1 to 2, we are like moving at a negative slope, right? We're accumulating at a decreasing rate. So that means that this guy is going to be concave down, our original function. So we can start getting an idea. We already have a few values. I know that -5 has an output of -26. I know that we have the ordered pair -3, 8. We have the ordered pair 634. And I'll just give you a few more just to like, if we were to plug in a -1, if we were to plug in a 2, if we were to plug in a 4. Ah, great. We found those points so quickly. Take a second and get these sketched and just graph the points, and then we'll do some connect the dots with some more information about this concavity. If you are someone who really struggled with the whole idea of graphing, this should feel a lot better because you're getting a little bit more information about what's going on. So you should feel more confident here, or that's like the hope. All right, I got my ordered pairs on. I also know, let's see, what did I say? We are concave up from -3 to -1. So I'm just going to kind of get that concavity drawn here. And then we're going to be concave down from -1 here. I'm going to assume that this is going at this downward rate. I also see that we're going to have some mins and maxes at these points, which makes sense, right? We're going from negative to positive. And then right here, I'm just going to kind of like, we're just going to throw some stuff in. We're decreasing, which means we'd be concave down from -5 to 3. So something like an idea of that. Just get some more information. It's lovely. So pulling this all together, we're able to start making some inferences with all this information. You guys have this reasoning and justification summary. This is really going to be an important thing to write down. We're going to do one more example, and I promise I will make it quick. We touched on this a little bit, but the whole idea of is in differential calculus, you use the derivative to discuss the properties of the function f. In integral calculus, we're almost reversing that idea, and we're using that derivative to talk about the antiderivative. So in this example below, we're saying that g is the antiderivative of f. Now, we're going to look at some of these relationships. we already can start defining a few things, right? We have these red intervals below the x-axis. So we can say like below x-axis, f is negative. We can also say, because there we have here, that when we are above x-axis, f is positive. So f is positive on the interval 0 to 8, so g is going to be increasing. And it's still kind of that same idea where you're like, you know your slope is positive, so we are increasing. I'm going to get this like written down here. So I'm going to say f increases, and g is also going to be concave up. Right here, we have f decreasing. So f decreases, and then g is concave down. We already looked at this a little bit. This guy's right here, these guys right here, oh, we're starting at 0, so we're not going to call him anything. This is going to be an extrema of g, because it's a 0 of f. And then right here, this maximum value, since this is technically a derivative function, this maximum value is going to be a point of inflection on g. So any maximum or minimum is now a point of inflection. So f changes signs at x equals 8. It is changing from positive to negative, right? Increasing to decreasing. So we're going to have a relative max because we're changing from positive to negative. The graph of g is decreasing where f is negative. And that's going to be values greater than 8. Since we are increasing from 0 to 4, we have that closed interval, then we are going to be concave up. And we are concave down where f is decreasing, which is going to be anything greater than or equal to 4. We have a max of 4, which means that like essentially, right, that double derivative is 0. So we have a point of inflection. Get this summary written down. You're going to be doing practice tomorrow, but please have this written down in your notes. It's going to be a really nice, important thing to go back and look. I'm going to drop some optional Khan Academy link here if you want to go to that. It is a great resource. It'll be in the comments of the video. Have a great day, guys.